A magnet can pull a paperclip without even touching it, and that feels like a superpower. So what's really doing the pulling? In this segment on how magnets work, we'll zoom way in, down to atoms, unpaired electrons, and tiny groups called magnetic domains. When enough of those line up, you get an invisible magnetic field with a north pole and south pole. And there's even a link to electricity. Ready? Start with the big idea. Magnets create an invisible magnetic field around them. That field is what reaches out and causes pushes and pulls. That magnetic field isn't magic. It comes from alignment across billions of atoms inside the material. Lots of tiny effects add together. Inside each atom, the spin of unpaired electrons matters. Their spin makes them act like tiny magnets at a microscopic level. Atoms don't act alone. They group into microscopic regions called magnetic domains, where many atomic magnets point the same general direction. In an unmagnetized object, magnetic domains point in many directions, so their effects cancel out. The overall magnetic field stays weak. Magnetize it, and the domains shift into alignment. Now they reinforce each other, creating a stronger combined effect you can actually notice. When enough domains align, the magnet ends up with two ends, a north pole and a south pole. That's how poles form. Those poles control interactions, opposite poles attract, but like poles repel. It's the same rule whether the magnets are big or tiny. So far, we've seen the chain, unpaired electron spin inside atoms forms magnetic domains, and alignment turns those domains into a strong magnetic field with north and south poles. That already explains why magnets can attract or repel without touching. But here's where it gets interesting. Not every object stays magnetized the same way, and heat can mess with the alignment. Then we'll end with the simple electricity connection. So what changes and why? Some materials make this easier. In iron, nickel, or cobalt, many electrons spin in the same direction, so lots of tiny magnets add up. Once aligned, the magnetic field extends beyond the object. That reach is why a magnet can affect things nearby, not just what touches it. That outside field can attract ferromagnetic materials. The magnet's field encourages alignment in the nearby material, so it gets pulled toward the magnet. A permanent magnet keeps its domains aligned even when nothing else is around. The alignment stays, so the magnetic field stays strong over time. A temporary magnet is different. A paperclip can act magnetized only when it's near a stronger magnet, because its domains don't stay aligned. Temperature effect matters too. Heating a magnet can disrupt alignment inside it, so the domains stop pointing together and magnetic properties weaken. One more stated link. Magnetism connects to electricity. A magnetic field is produced whenever an electric charge moves, even though we're not detailing how. Now you can explain the invisible force without hand waving. Magnets work because unpaired electron spin makes atoms act like tiny magnets, and magnetic domains can line up. When they do, you get a magnetic field with a north pole and south pole. So opposite poles attract and like poles repel. The field can reach out and pull ferromagnetic materials, and a paperclip can become a temporary magnet. Heat can disrupt alignment, and moving electric charge produces a magnetic field too. Thanks for watching. If this made you curious, leave a question or topic you want explained next in the comments. I'm turning everyday questions into short explainers, so subscribe if you want to see more.